In the last video, we were introduced to single lens systems, and now I'd like to extend that to multiple lens systems as we eventually look towards doing things like talking about how to make telescopes and microscopes. So remember, the way you solve any physics problem goes by the mnemonic STAR: situation, tools, answer, review. And the first step of sussing out the situation is always to draw a picture. In the case of optics problems, it's definitely to draw a ray diagram. And this is because if you draw it to scale, that literally is the answer. You can just read it right off the drawing. You don't need to do any more math than that. However, if you aren't quite so careful with your drafting skills, at least as long as you do a pretty good job, you'll have a very good sense of what the answer ought to be, and it'll also help set things help you to check your work and to help set things up for next steps. So with a multiple lens system, the only new wrinkle, which I will justify retroactively, is that you treat things one lens at a time, and you use the image from lens number 1 to be the object for lens number 2. So with that, let's go ahead and take a look at a system here where I've got two lenses. So just drawing the principal planes. There we go. And we'll make this lens here a converging lens, and we will give it a focal length of 5 centimeters. So we'll go ahead and just kind of color code that off a bit. So the we're going to have a 12 centimeters spacing between these, so we'll dimension that in. So 5 centimeters would be not quite halfway. So let's use purple for the first lens here. Yeah, that looks like maybe that, and then kind of match it over there. All right, so I have dimensioned off both focal points for lens number 1. So we will label that as F1 equals plus 5 centimeters because it's a converging lens. Our other lens, 12 centimeters away from the first one, will be a diverging lens. There we go. And we'll say that its focal length is -8 centimeters. So, so this would be 7 centimeters away. Since this is 5 centimeters from here and this is 12 centimeters, this is 7 centimeters. So if we go ahead and mark this one here, let's use, I don't know, red, maroon, I guess. This would be one of our focal points, and then we need to do just about as far the other way. So let me extend our optical axis out a bit. Oops. There we go. And we'll go ahead and draw in those dimensions. Now, since this is a diverging lens, the focal lengths here are negative, which, remember, means that the roles of the focal points are reversed. All right. So now let's go ahead and say that we have placed a object that is 1 centimeter high, 4 centimeters in front of the first lens. So that's going to be in about, whoops, it's going to be about there, something like that. So since we will have multiple object and image distances, we will call this one S1. And we are noting that is 4 centimeters. And we will go ahead and dimension off its height. And again here, because we'll have multiple heights to keep straight, we'll call this H1 is +1 centimeter. Okay, and so what we want to know is where will the final image due to the pair of lenses be located, and what will its final height be? So following our usual rule of thumb here, we will go ahead and draw the ray diagram. So here is the paraxial ray. And it will go out through the focal point, and make sure you keep your focal point straight. Now notice, whoops. Now notice here that I am not drawing the ray all the way. I'm just going to be drawing it enough to locate the image, and this is just because I want to reduce clutter. Of course, this ray is going to pass through this lens, but since it isn't one of the 3 special rays, it's not going to be too helpful for us. All right, let's go ahead and do the central ray because it's our truest, bestest friend. And again, I'm not drawing it very long. And the reason is I know that the image is going to be virtual. This is because S1 is less than F1, which makes this and it's a converging lens, so that makes this case 3. So I already know that the image that the first lens makes, what we will call the intermediate image, will be virtual, upright, and magnified. So I don't really need to extend these rays any further than I have to, because all I need to do is locate the image, which I know will be to the left. Now with the focal ray, because the focal ray is going to go out parallel, it will become the paraxial ray for the next lens. So I will draw more of it. So there it is, heading away from the focal point, and it is heading out, whoops, parallel, and I'm just going to go ahead and take this all the way over to the next focal plane because this is going to become the next lens's paraxial ray. Well, all right. Now all we have to do is go ahead and backtrack the rays. Something like that. Something like that. And okay. Yeah, I knew that red one was sketchy. That's why you draw 3 rays, so that you can double check your art. There we go. That looks better. All right. So we have located what we will call the intermediate image. So what we will do is we will calculate where it's located at. And then the rule is that this image here will be the object for this lens here. Now when we draw the ray diagram using this as the object for this lens, we will be completely ignoring this lens. We'll just be drawing our lines right through it. And that is because we are really following the journey of these lines here. So we have already taken this lens into account. All right, but let's go ahead and calculate where it's going to be. So We can start with the most useful equation in optics, 1 over s plus 1 over s prime equals 1 over f. And we can rearrange that to get 1 over s prime equals 1 over f minus 1 over s, put on a common denominator, s minus f over sf. So this will give us s prime equals sf over s minus f. All right, so now here, since we will be reusing this for the second lens, so it's a good thing we did this all in letters first. Now let's go ahead and get the numerical value for the first image position, and this will be measured from the principal plane of the first lens. So S1 is 4 centimeters, plus 4 centimeters. F is plus 5 centimeters, and this will be over plus 4 centimeters minus plus 5 centimeters. So this will be located at minus 20 centimeters. Now while we're at it, let's go ahead and find the image height. So we remember that the lateral magnification, which is h prime over h, is also equal to minus s prime over s. So h prime will be minus s prime over s times h. So here, this will give us h1 prime is going to be minus, our s1 prime here is minus 20 centimeters. Make sure to keep both minus signs. Our s was 4 centimeters. And then we said that our initial height was plus 1 centimeter. So h1 prime is plus 5 centimeters. All right, so we can go ahead and dimension those off. So this height here is going to play double duty. This is h1 prime, but since it'll be the object for lens number 2, this is also h2, and this we said was plus 5 centimeters. We also worked out that this distance here, s1 prime, was minus 20 centimeters. Now, the only bit of trickiness here, if there is a trick, is to get the right distance for S2. Because remember, you always measure from the lens in question. So this distance right here, from here to here, this will be my S2, and I'm just leaving some space here. And if we look at this, we know that it's bigger than 20 centimeters. Yeah, I know this isn't very well to scale. And we know that this is 12 centimeters. So this has got to add up to 32 centimeters. And the way this is going to work is this is L minus S1 prime. So this will be 12 centimeters minus a negative 20 centimeters is plus 32 centimeters. If you draw a half reasonably dimensioned drawing, you end up, you can then figure out whether you should be adding or subtracting just by using your common sense. You know it's got to be bigger than 20, you know it's got to be bigger than 12. The only way that's going to happen is if you subtract that negative there. So, all right, we have figured out our S1 prime, and so now we're ready to go. So now let's go ahead and draw our next ray diagram. So I'll try to use different shades of roughly the same color. So you start here. So for the paraxial ray, like I said, we already drew it. So there it is. You know, coming off of here and going to here, and we just totally ignored this lens here. And it's going to go away from that lens there. And again, because this is a diverging lens, I already know this is case 4. So I know that the image will be virtual, upright, and minified. But minified with respect to this. How it compares to the original object height, we'll just have to do some math. Spoiler alert, it's a bit of a Shaggy Dog story. All right, So then let's go ahead and do the central ray. Yeah, that's sort of a subdued orange. So the central ray is again your truest, bestest friend. And it will go through, there we go, undeflected. And it also just does its own backtracking for you, which is awesome. So we already know where the image is. It's going to be right there. But let's double check that with the focal ray. So remember, with a diverging lens, the focal ray is going to be aimed at this focal point here. So let's see, the focal ray should be red, or sorry, oh, my bad. This should have been red here. Oh, well, sorry about that. What do we want to make our focal ray then? Let's make our focal ray whatever that color is. So our focal ray will be aimed at this point right here. So I am going to do it like that. And then I am going to just very gently erase it right there. And then I'm going to make that go away. There we go. And then we can finish off with dots just to remind ourselves the way it was headed. But this is not a backtracking ray. All right. And this ray will go out parallel. So we can go ahead and backtrack. And sure enough, there it is. And that is our final image right there. Now, I promised that I would, in hindsight, I would retroactively justify how we could get away with saying, oh, the image of the first is the object of the second. Because really, the light is coming from here. It's not coming from here. It originates here, and it got bent through this lens, and then it got bent through this lens. So why can we get away with doing this construction? Well, what this construction was really doing was it was allowing us to identify, what's a good color here? Yeah, purple, I guess. Oh, here, there we go. It was allowing us to identify these two rays right here. These rays aren't particularly special rays for lens number 1, but they are the rays that bend at this principal plane to become the special rays for lens number 2 to allow us to go ahead and locate the image there. So that's really all this construction was doing, was finding these real rays right here, these actual rays right here, that would refract here and here. But since they weren't special rays, they weren't easy to figure out. By computing this intermediate image, we can figure out the effective path of these rays. Now, in practice, nobody ever bothers drawing these rays in. I was just doing this to retroactively justify why we could do this. All right, so with that, we can go ahead and figure out our S2 prime. And we can do that by just literally recycling that result right there. Just being careful about our S1 prime distance. So S2 prime is going to be our new object distance was plus 32 centimeters. Because remember, we were measuring from in front of lens number 2. The focal length is -8 centimeters, subbing into there. And so we will say over plus 32 centimeters minus a -8 centimeters. This works out to be minus 6.4 centimeters. So we have located our image here to be 6.4 centimeters in front of the second lens. All right, and then let's get our height. So for our height, it's going to be the same thing. We're just going to recycle this result, although we use the height of the first image as the height of our second object. So we will say h2 prime will be minus, okay, our s prime we said was minus 6.4 centimeters. Our s was plus 32 centimeters. And we had a plus 5 centimeter height. Well, this turns out to be 1/5. So our height turns out to be exactly 1 centimeter. So all this did was bring we have a image of the exact same height, but we brought it closer. Now this might be useful in a camera system because it would take up a bigger angle in the field of view. So even though the lateral magnification is the same, the angle you take up is bigger, and so we would say that we have increased the angular magnification, which we will be getting to later. Okay then, so in the next video, we will start taking a look at cameras and eyes. Catch you over there.